Everything in our world is made up of matter. The computer you are using, the air you are breathing, the rain outside, and even your body are all examples of matter. In fact, anything that has mass and occupies space is matter. All matter is divided into three states: solids, liquids, and gases. Solids, such as your skeleton, your computer, a book, and a pencil, are in a state of matter that has a definite shape and volume. Liquids, such as raindrops, milk, and tea, are states of matter that have definite volume but indefinite shape. Gases, such as oxygen, helium, and carbon dioxide, are states of matter that have indefinite shape and volume and are what will be discussed in this program. Air is commonly used as an example of a gas, but it's actually a mixture of several gases, including oxygen, nitrogen, and small amounts of other gases, such as carbon dioxide and argon. Air is used in the internal combustion engine of automobiles and is used to drive power tools, such as jackhammers. Air is also used to fill car tires, bicycle tubes, air mattresses, balloons, and balls used in sports and other activities. Air carries sound, such as music or people's voices. Air also carries scents, such as the smell of popcorn or food cooking on your neighbor's barbecue. Nitrogen gas fills automobile airbags, which save lives in car accidents. Natural gas is used to heat houses and is used in gas stoves for cooking. Propane gas is used in your barbecue. Heated gases are what allow hot air balloons to fly. Scuba divers use a mixture of gases for breathing underwater. Without the presence of gases, there would be no life. You must breathe in oxygen gas and exhale carbon dioxide gas in order to stay alive. Plants are just the opposite. They require carbon dioxide gas and release oxygen gas. As you can see, gases are a very important part of this world. This program will explore the properties of gases, the laws that describe the behavior of gases, and how chemists explain these behaviors. Before starting an in-depth study of gases, it is important to understand that gases are a form of matter, and therefore they have mass and occupy space. A couple of simple experiments can be done to convince you that gases do indeed have mass and occupy space. To show that gases have mass, weigh a deflated volleyball on a sensitive balance. Fill it with air, and then weigh the inflated volleyball. The weight of the air inside the volleyball can be found by subtracting the weight of the deflated ball from that of the inflated one. The weight of the air inside the ball is 5.40 grams. As you can see, air has mass. Remember from the previous scene that air is a mixture of gases. The total mass of each gas contributes to the total mass of air. Do gases also occupy space? An experiment using air as gas shows you that gases do indeed occupy space. In this experiment, a piece of paper is crumpled up and taped to the bottom of a beaker. The beaker is inverted and placed in a dish of water. The piece of paper does not get wet because the air inside the beaker prevents the water from entering the beaker. Tipping the beaker sideways allows the air inside the beaker to escape and be replaced with water, which wets the paper. The bubbles you see are evidence of the escaping gas. Air, like all gases, is a type of matter because it occupies space and has mass. From the previous demonstrations, you should be convinced that gases have mass and occupy space. Knowing this, you will start your study of gases by exploring the physical properties common to all gases. Physical properties are the properties of a substance that can be observed and measured without chemically changing the substance. To completely describe gases, 4 factors must be discussed. These factors are volume, temperature, pressure, and quantity of a gas. They will be defined, explained, and then used to help you understand the physical properties of gases. First, when talking about gases, one must specify how much gas they are referring to. This is called the quantity of a gas, abbreviated N, and is measured in moles. As you may have learned, a mole contains 6.02 times 10 to the 23rd particles. Therefore, a mole of oxygen gas contains 6.02 times 10 to the 23rd molecules of oxygen. The number 6.02 times 10 to the 23rd particles per mole is known as Avogadro's number. The next factor used to describe gases is volume, abbreviated V. Volume is the space matter occupies and is often measured in liters. Earlier you saw experiments that prove gas is a type of matter because it has mass and occupies space. Furthermore, gases are defined as matter that has indefinite shape and indefinite volume. Indefinite shape means that gases do not hold their own shape. Instead, they take the shape of their container. This can be seen by blowing air into different shaped balloons. The amount of gas, in this case air, that fills each balloon is the same, but the shape of the balloon, and therefore the shape of the gas, is different. Gases also have indefinite volume. This means that gases do not have a set volume, but instead completely fill the entire volume of their container. For example, if a sample of gas is placed in a 1-liter container, the gas will completely fill the entire liter. If that same sample of gas is then transferred to a 2-liter container, it will spread out even more to completely occupy both liters. Depending on its container, the sample of gas has different volumes. Solids and liquids, on the other hand, have a definite volume, which means that their volume is always the same even if they are placed in a larger container. Because a gas fills up the entire volume of its container, the volume of a gas is taken as the volume of the container in which it is placed. If a gas is not held within a closed container, its volume cannot be determined because it spreads throughout the entire room and eventually into the atmosphere. This happens because each particle of a gas is constantly moving. Each gas particle moves at a high speed in a straight line, changing directions only when it collides with something. This constant movement of gas particles explains why you can smell food when you are far away from it. For example, you can smell popcorn when you walk near a movie theater because the gas particles responsible for the popcorn smell move quickly through the air and eventually reach your nose. The ability of a substance to completely spread out and mix with other substances is called diffusion. One of the properties of gases is that they diffuse very easily. For example, when you open a container of ammonia, the gas particles quickly diffuse throughout the room and therefore can be smelled by people on the other side of the room. The ability of gases to diffuse also explains their indefinite shape and indefinite volume. Because gases do not have definite volume, they can be squeezed or forced into smaller volumes. The ability to force gases into smaller spaces is a property known as compressibility. A bicycle pump, for example, works by compressing air as it forces it into bicycle tubes. When the handle of a bicycle pump is raised, air is drawn into the pump, and as the handle is pressed down, the air is compressed or squeezed into a smaller volume. This compressed air then goes into the bicycle tube. A bicycle pump, like this, uses physical strength to compress air. Devices that use electrical power to compress air are called air compressors. Air compressors are commonly used to power tools such as jackhammers and are used to fill car tires, inner tubes, and air mattresses. When camping, many people sleep on air mattresses because they are more comfortable than sleeping on the ground. The weight of a person lying on an air mattress forces the air to compress slightly, but still allows a soft cushion between the weight of their body and the uncomfortable rocks and sticks below. The third factor used to describe gases is temperature, which is abbreviated T. Temperature is usually measured with a thermometer in degrees Celsius. When studying gases, it is also important to know the Kelvin temperature scale. Look at the two thermometers. The one on the left is the Celsius scale, and the one on the right is the Kelvin scale. 0 degrees Celsius equals 273 kelvins, and 0 kelvins equals negative 273 degrees Celsius. It is also important to note that the degree symbol is not used with Kelvin temperatures. Conversions between degrees Celsius and kelvins can be made using the formula temperature in kelvins equals the temperature in degrees Celsius plus 273. For example, what is the Kelvin temperature of 25 degrees Celsius? Substituting 25 into the degrees Celsius and adding 273, you find that 25 degrees Celsius equals 298 kelvins. How many degrees Celsius is 250 kelvins? Substituting 250 kelvins into the equation, you find that 250 kelvins is negative 23 degrees Celsius. You will learn more about the significance of this Kelvin scale later in the program. The final factor used to describe gases is pressure, abbreviated capital P. You are probably already familiar with the term pressure. In everyday conversation, perhaps you have talked about tire pressure, atmospheric pressure, pressure cookers, or water pressure. Perhaps you have experienced how changes in atmospheric pressure cause your ears to pop when you drive up into or down from the mountains. Have you ever blown up a balloon? If so, then you have had experience with air pressure. Air pressure is what gives a balloon its shape. But what exactly is pressure? Pressure is defined as force exerted on an object per unit area. The pressure inside a balloon is due to the force of the gas particles striking the inside of the balloon. But what exactly is force? Force is anything that causes an object to move, change its speed, or change its direction. For example, gravitational force is what causes objects to move toward the Earth. When a book is dropped, the gravity pulls the book toward the Earth. This gravitational pull of the mass of an object is what gives an object its weight. Because gravity is always acting, the force of an object on Earth is known as the weight of the object. Therefore, in the equation for pressure, the weight of an object can be used as the force. Take a look at the following examples of pressure and force. Pressure is force divided by area, and as you learned in the previous scene, the force on an object due to gravity is the weight of the object. For objects on Earth, pressure can be weight divided by area. For example, a bucket of water might have a weight of 10 kilograms. When this woman puts the bucket on her head, she feels the pressure the bucket of water exerts against her head. If the area of her head that contacts the bucket is 35 square centimeters, what is the pressure she feels? The pressure is the weight of the bucket, 10 kilograms, divided by 35 square centimeters. The pressure felt by the woman is 0.29 kilograms per centimeter squared. A child who carries the same bucket of water feels a greater pressure because the area of the child's head is smaller, while the weight of the bucket of water is the same. If the area of the child's head is 20 centimeters squared, then the pressure the child feels is about 0.50 kilograms per centimeter squared. Just as the bucket of water exerts pressure on the head of the person who carries it, gases exert pressure on the containers that hold them. Gas pressure is due to all the gas particles colliding with the inner surface of the container in which they are held. These gas particles are moving in all directions, and therefore gases exert pressure in all directions. In the previous two scenes, you saw that gravity acts on all objects and that the measurement of an object's mass with respect to the pull of gravity gives an object its weight. This weight divided by the area over which it acts is known as pressure. What about air? At the beginning of the program, you saw that air has mass. Just like all other objects, gravity pulls air toward the Earth. The result of gravity pulling the particles in the air toward the ground is known as atmospheric pressure. In fact, at sea level, a force slightly greater than 101,325 newtons per square meter is exerted on objects, including humans. A force of 100,000 newtons is the same as the force exerted by an object with a mass of 9,070 kilograms or 10 tons. You don't feel this force, however, because the human body exerts an equal outward force. To get an idea of how powerful atmospheric pressure is, take a look at the following demonstration. Atmospheric pressure is striking this can in all directions. The can does not collapse, however, because there is air inside the can exerting the same pressure, but in the opposite direction. Watch what happens as water inside the can is boiled, creating steam, which displaces the air. When the can is inverted and placed in water, the steam condenses and returns to the liquid state. This creates a vacuum, and the can is crushed because the pressure inside the can is less than the atmospheric pressure outside the can. In effect, the atmospheric pressure striking the can from the outside is powerful enough to crush it. Atmospheric pressure is measured with a barometer. A simple barometer, like the one seen on your screen, consists of a glass tube sealed at one end, filled with mercury and turned upside down onto a dish of mercury. The atmospheric pressure pushes down on the mercury and causes the mercury to rise into the glass tube. The height of the mercury, measured in millimeters of mercury, indicates atmospheric pressure. The units millimeters of mercury are also called torr, named after Evangelista Torricelli, who invented the mercury barometer in 1643. Atmosphere, abbreviated ATM, is another unit to measure pressure. 1 atmosphere of pressure is equal to 760 millimeters of mercury and 760 torr. In addition, atmospheric pressure is sometimes reported in the unit bar, and 1 atmosphere equals 1.013 bar. At sea level, atmospheric pressure is 101,325 newtons per square meter or 1 atmosphere, but as altitude increases above sea level, atmospheric pressure decreases. For example, at the top of Mount Everest, which is about 9 kilometers high, atmospheric pressure is approximately 0.3 atmospheres. While barometers are used to measure atmospheric pressure, a different type of instrument, called a manometer, is used to measure the pressure of gases in closed containers. An opened-end manometer, like the one on your screen, is attached to a gas-filled container, and mercury is inside the U-tube, which is open to the atmosphere. The pressure exerted by the gas in the container is determined by reading the height of the mercury in the U-tube. If the mercury level is the same on both sides, then the gas pressure is the same as the atmospheric pressure. If the level of mercury is higher on the open end, then the gas pressure is greater than the atmospheric pressure. The value of the gas pressure is determined by adding the difference of the two heights to the atmospheric pressure. If the level of mercury is higher on the side with the enclosed gas, then the gas pressure is less than the atmospheric pressure. The value of the gas pressure is found by subtracting the difference of the two heights from the atmospheric pressure. In our discussion of barometers and manometers, you have seen that pressure can be measured in units of millimeters of mercury, torr, atmosphere, and bar. The System International, or SI unit for pressure, is the pascal, abbreviated PA, which has units of force per area. 1 pascal equals 1 newton divided by 1 square meter. The unit pascal clearly illustrates the definition of pressure as force divided by area because newton is a unit of force and meter squared is a unit of area. 1 atmosphere is equal to 101,325 newtons per square meter or 101,325 pascal. Since a pascal is very small, kilopascals are generally used instead. 101,325 pascals equals 101.325 kilopascals. You may be familiar with pressure gauges that report pressure in PSI, which stands for pounds per square inch. 1 atmosphere is equal to 14.7 pounds per square inch. Because there are so many different units for pressure, it is very important to be able to convert between different units of pressure. For example, suppose you need to know how many atmospheres there are in 950 millimeters of mercury. As you will see in the next scene, this can be done using conversion factors. To determine how many atmospheres there are in 950 millimeters mercury, you must know that 1 atmosphere is equal to 760 millimeters mercury. To do the conversion, organize the information as shown on the screen. In the top left-hand corner, write what you are starting with. In this case, 950 millimeters mercury. Now, place the conversion factor in the right-hand side of the table, placing the units you want to determine, in this case atmospheres, on top, and the unit you are trying to get rid of, in this case millimeters mercury, on the bottom. Just like numbers, units that are the same on the top and bottom cancel. Now do the math. 950 millimeters mercury times 1 atmosphere divided by 760 millimeters mercury is 1.25 atmospheres. Therefore, 950 millimeters mercury is equal to 1.25 atmospheres. The trick for doing conversions is to set them up so that the unwanted units cancel, leaving you with the units you need in your answer on top. Once that is done, do the math and you'll have the answer. Here are 2 more examples. How many kilopascals are in 2 atmospheres of pressure? The conversion factor is 1 atmosphere equals 101.325 kilopascals. Start with the information you are given, 2 atmospheres. Now multiply by the conversion factor arranged so that atmospheres are on the bottom and kilopascals are on top. Canceling the units and doing the math, you find that 2 atmospheres equal 203 kilopascals. Suppose you are asked to convert 1520 torr to bars. Start with the information you are given. Now use conversion factors to get your answer into bars. Since the table does not contain the direct conversion from torr to bar, you must first convert torr to atmosphere, then convert atmosphere to bar, so that all units cancel. Doing the math shows that 1520 torr equals 2.026 bar. Remember that one of the properties of gases is that they exert pressure. Another property of gases is that the pressure a given amount of gas exerts depends on the temperature of the gas. Have you ever noticed the warning on aerosol cans stating never dispose of the can in a fire? The label is placed on the can because a heated can may rupture violently and cause injury to those near the explosion. This happens because as the gases inside the can increase in temperature, the pressure inside the can increases. Eventually, the internal pressure overcomes the strength of the can, causing it to explode. Similarly, on very hot days, the increase in temperature causes the air pressure in automobile tires to increase. On very cold days, the opposite happens. A car owner may have to add air to the tires because the decrease in temperature causes the air pressure to decrease. From these examples, you can see that the pressure exerted by a gas changes with temperature. Therefore, pressure and temperature are related. In the previous scene, you saw that pressure and temperature are related. In fact, all the factors used to describe gases are interrelated. Just as you have become familiar with properties of gases, scientists in the 17th, 18th, and 19th centuries were also aware of the physical properties of gases. To learn more about how gases behave, these scientists conducted many experiments which led to the discovery of the gas laws that describe the relationships between pressure, volume, temperature, and the amount of a gas. In science, a law is a way of describing behavior that always works in the same way under the same conditions. These behaviors are formed into laws only after they have been observed and tested in many experiments. Scientists found the gas laws could describe the behavior of most gases. In the 17th century, Robert Boyle, an Irish chemist, studied the relationship between pressure and volume in gases. In his experiments, he used a J-shaped tube to measure the volume of trapped gases at different pressures. His results were similar to the data shown on your screen. As you can see, when the pressure increases, the volume decreases. The opposite is also true. When the pressure decreases, the volume increases. These experiments led to Boyle's law, which states that at constant temperature, the pressure of a given amount of gas is inversely proportional to the volume of the gas. The term inversely proportional means that when one increases, the other decreases. Factors that are inversely proportional or directly proportional to each other can be turned into equations by multiplying by a constant. Boyle's law can be expressed as the equation pressure equals a constant C subscript B times 1 divided by the volume. 1 divided by the volume is written because the pressure and volume are inversely proportional. Later in the program, you will see how variables that are directly proportional are written. Multiplying both sides by V, you can see that pressure times volume equals a constant. Take a look at the data given earlier. Does the pressure times the volume equal a constant? The answer is yes. In each experiment, pressure times volume is constant. In this case, each trial has the value of 6. Boyle's law can be written in another way, which allows you to calculate the pressure or volume of a gas without having to do an experiment. Take a look at how this is done. First, recall that Boyle's law states that for a given amount of a gas at a constant temperature, the pressure times volume equals a constant. This can be written as P1 times V1 equals a constant C subscript B1. Now let's assume you have a different pressure and volume, but the temperature and the number of moles remain the same. This new set of data can be written P2 times V2 equals a constant C subscript B2. Because both sets of data were collected at the same temperature and have the same number of moles, constant 1 and constant 2 are equal. As a result of the constants being equal, P1 times V1 must equal P2 times V2. If any 3 of these variables are known, the fourth can easily be calculated. For an example of how Boyle's law is used, consider the following scenario. If a balloon filled with 2.50 liters of helium at a pressure of 1 atmosphere is released into the sky, what will the volume of the balloon be when it rises to an altitude where the pressure is 0.900 atmospheres, assuming a constant temperature? To solve this problem, you can use the equation P1V1 equals P2V2. Assign each variable in the equation to its corresponding quantity given in the problem. The initial volume, V1, is 2.50 liters, and the initial pressure, P1, is 1 atmosphere. After the balloon is released and rises high into the air, the conditions change. Here the new pressure, P2, is 0.900 atmospheres, and you want to solve for the new volume, V2. Now that you have the values of three variables, substitute them into the equation and solve for V2. Solving for V2, you get 2.50 liters times 1 atmosphere divided by 0.900 atmosphere. Doing the math, you will find that the volume of the balloon at a pressure of 0.900 atmospheres is 2.78 liters. Boyle's law states that for a given amount of gas at a constant temperature, pressure and volume are inversely proportional. What is the relationship between volume and temperature for a given amount of gas when the pressure is held constant? To determine this, a balloon inflated at room temperature has liquid nitrogen, which has a temperature below negative 195.8 degrees Celsius poured over it. The balloon shrinks, or more specifically, the volume of the air inside the balloon decreases, causing the balloon to shrink. When the balloon is allowed to return to room temperature, the air inside it expands. This experiment shows that a decrease in temperature causes a decrease in volume, and an increase in temperature causes an increase in volume. As you can see, volume is directly proportional to temperature. In the 18th century, a French physicist and balloonist discovered this exact relationship, which is now known as Charles's law. Charles's law states that the volume of a given amount of gas at constant pressure is directly proportional to its temperature on the Kelvin scale. During his research, Charles graphed his data as volume versus temperature and found that the data for each gas yielded a straight line. When each line was extended to a volume of 0, all the different gases intersected at negative 273 degrees Celsius. The observation of this unique temperature on the Celsius scale, at which the volume goes to 0, suggests that a new temperature scale would be helpful. This temperature is known as absolute zero, since it is theoretically the lowest temperature that can be reached. In order to have an absolute temperature scale, the Kelvin temperature scale was created using absolute zero as 0 kelvins. A temperature below absolute zero is impossible because a gas can never achieve a negative volume or even a volume of 0. Although absolute zero has never been achieved, experiments have been performed where temperatures within a millionth of a degree above absolute zero have been recorded. As mentioned earlier, Charles's law states that the volume of a given amount of gas at constant pressure is directly proportional to its temperature in kelvins. A proportional relationship can be changed into an equation by inserting a constant, and Charles's law can be expressed as volume equals a constant times temperature in kelvins. Charles's law can be rearranged by dividing both sides by temperature. This gives volume divided by temperature equals the constant C subscript C. As long as the pressure and number of moles remain the same, the constant C subscript C will also be the same even if volume and temperature change. Therefore, V1 divided by T1 equals C subscript C1, and V2 divided by T2 equals C subscript C2. Constant 1 and constant 2 are the same, so Charles's law can be expressed as V1 divided by T1 equals V2 divided by T2. This equation allows you to calculate any variable when the other three are known. For example, if a balloon is filled to a volume of 3.5 liters at a temperature of 45 degrees Celsius, what will the new volume be when the balloon is taken inside an air-conditioned room at 25 degrees Celsius? The starting conditions are V1 is 3.5 liters and T1 is 45 degrees Celsius. Remember that a Kelvin temperature must be used, so 45 degrees Celsius must be converted to kelvins, which can easily be done by adding 273. This yields the temperature 318 kelvins. When the balloon is taken inside, the new temperature is 25 degrees Celsius, which converts to 298 kelvins. So now the new volume can be calculated. Substituting all the numbers in the equation and doing the math, you find that the volume of the balloon inside the air-conditioned building is 3.3 liters. Boyle's law and Charles's law can be combined to form an equation called the combined gas law. The combined gas law is P1V1 divided by T1 equals P2V2 divided by T2. If the temperature is held constant, you are left with Boyle's law, P1V1 equals P2V2. And if the pressure is held constant, you are left with Charles's law, V1 divided by T1 equals V2 divided by T2. The combined gas law is useful because it allows you to perform experiments in which the pressure, volume, and temperature change, but the moles of gas remain constant. The combined gas law can be used to solve the following problem. Nitrogen gas is stored in a container with an initial volume of 3 liters at a pressure of 1 atmosphere at 25 degrees Celsius. Decreasing the volume causes the pressure to increase to 1.6 atmospheres and the temperature to increase to 45 degrees Celsius. What is the new volume? First, match the numbers in the question to the variables. V1 is 3 liters, P1 is 1 atmosphere, and T1 is 25 degrees Celsius, which is 298 kelvins. After the volume is decreased, the pressure, P2, is 1.6 atmospheres, and the temperature, T2, is 45 degrees Celsius, which is 318 kelvins. V2 is the new volume, which must be calculated. Second, solve for V2 by moving T2 and P2 to the other side of the equation. Third, substitute all the numbers into the combined gas law equation. Using a calculator, you find that V2 equals 2 liters. The combined gas law shows the relationship of pressure, volume, and temperature when the number of moles of gas remains constant. What happens when the number of moles of gas changes? An Italian chemist, Amedeo Avogadro, studied the relationship between the number of moles of a gas and its volume. He found that all gases with an equal number of particles also have equal volumes when the pressure and temperature are held constant. Increasing the number of gas particles increases the volume, and decreasing the number of molecules decreases the volume. This led to Avogadro's law, which states that at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of the gas. Avogadro's law can be illustrated by blowing up a balloon. Blowing air into a balloon increases the number of air particles in the balloon, and as you can see, the volume of the balloon also increases. Because the volume of the gas is directly proportional to the number of moles of the gas, Avogadro's law can be expressed as the equation volume equals the number of moles, N, times a constant, C subscript A. This can also be written as volume divided by the number of moles equals the constant C subscript A. As long as the temperature and pressure remain the same, the constant C subscript A will always be the same. Avogadro's law can therefore be written as V1 divided by N1 equals V2 divided by N2. For Avogadro's law to apply, temperature and pressure must be constant. To provide a frame of reference, many measurements are reported at 0 degrees Celsius and 1 atmosphere of pressure. This specific temperature and pressure is called standard temperature and pressure and is abbreviated as STP. At STP, a mole of any type of gas occupies 22.4 liters, which is known as standard molar volume. Standard molar volume and Avogadro's number are useful for converting between liters, moles, or particles. For example, how many oxygen molecules are in 2.3 liters of oxygen gas at STP? Using standard molar volume as the conversion factor, you can determine that 2.3 liters contain 0.1027 moles. Avogadro's number is used next to convert from moles to particles. 0.1027 moles of oxygen gas contains 6.18 times 10 to the 22nd molecules of oxygen. Standard molar volume can also be used to solve questions, such as what is the volume of 0.402 moles of a gas at STP? Using standard molar volume as the conversion factor, you find that 0.402 moles of a gas takes up a volume of 9 liters. These calculations can be taken a step further by converting between moles and grams. From your previous studies in chemistry, you should recall that moles can easily be converted to grams using the molecular mass of the substance. How many grams of oxygen are in 0.103 moles? The molar mass of an oxygen atom is 16 grams per mole, so molecular oxygen, containing 2 oxygen atoms, has a molar mass of 32 grams per mole. Multiplying this by the number of moles, you find that 0.103 moles of oxygen has a mass of 3.3 grams. Methane, the chief component of natural gas, reacts with oxygen to form carbon dioxide, water, and heat. In a Bunsen burner, how much oxygen is needed to completely burn 12 liters of methane? Because the gas laws can work for a variety of gases, this question can be answered using Avogadro's law. V1 divided by N1 equals V2 divided by N2. From your previous study of chemistry, you are probably already aware that the coefficients in the balanced chemical equation represent the number of moles of each compound. You are given the volume of methane to be 12 liters, so assign that value to V1. Looking at the balanced equation, there is only 1 mole of methane, so N1 equals 1, and there are 2 moles of oxygen, so N2 equals 2. Now, the values can be plugged into the equation, and the equation can be solved for V2, which represents the volume of oxygen needed to completely burn 12 liters of methane. Solving the equation, you should find that 24 liters of oxygen are required to completely burn 12 liters of methane. Now it is time to relate all 4 factors used to describe gases into one equation. This can be done by combining the 3 gas laws you have just learned. Remember, Avogadro's law states that volume is proportional to number of moles of gas. Charles's law states that volume is proportional to temperature, and Boyle's law states that volume is inversely proportional to pressure. Putting these together, you find that volume is proportional to the number of moles times the temperature divided by pressure. Like all proportions, this can be changed into an equation by inserting a constant. The universal gas constant, symbolized by the letter R, is inserted, and both sides are multiplied by P to give PV equals nRT. This equation is called the ideal gas law. The ideal gas law describes the behavior of ideal gases. As you will learn later in the program, there is no such thing as an ideal gas, but at pressures near 1 atmosphere or less, and at room temperature, most gases behave ideally. In order to use the ideal gas law, the value of the universal gas constant must be known. It can be calculated by inserting standard temperature, pressure, and volume for 1 mole of gas into the equation. Standard temperature is 273 kelvins, pressure is 1 atmosphere, volume is 22.4 liters, and there is 1 mole of gas. Rearrange the ideal gas law to solve for R. Then plug these values into the equation and solve. The universal constant has a value of 0.0821 liters atmosphere divided by Kelvin mole. Using the value of R, the ideal gas law can be used to calculate the 4th factor when the other 3 variables in the equation are known. For example, how many moles of propane gas, C3H8, are contained in a 20-liter tank at a pressure of 3 atmospheres at 25 degrees Celsius? This can be determined using the ideal gas law PV equals nRT. From the question, you know that the volume is 20 liters, the pressure is 3 atmospheres, the temperature is 25 degrees Celsius, which converts to 298 kelvins, and the universal gas constant is 0.0821 liter atmosphere divided by Kelvin mole. The only unknown is the number of moles. Rearrange the gas law to solve for N. Next, substitute the values into the equation and solve. There are 2.5 moles of propane gas. The ideal gas law does not specify the identity of the gas. Sometimes gases are pure, but oftentimes mixtures of gases are used. How does the ideal gas law account for gas mixtures? The English chemist John Dalton discovered the answer to this. He found that each gas in a mixture exerts the same pressure as it would if it were in a container by itself. The pressure exerted by each component of the mixture, called partial pressure, is added together to find the total pressure exerted by the gas mixture. For example, the partial pressure of gas A, gas B, and gas C can be added together to find the total pressure of the mixture, in this case 1400 kilopascals. This discovery is known as Dalton's law of partial pressure, which states that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of each gas in the mixture. This is expressed mathematically as P subscript total equals P subscript A plus P subscript B plus P subscript C, and so on. Air is a mixture of gases containing nitrogen, oxygen, and small amounts of other gases, such as carbon dioxide and argon. In a sample of air at sea level, the partial pressure of nitrogen is 0.781 atmospheres, oxygen is 0.210 atmospheres, and the partial pressure of other gases combined is 0.009 atmospheres. What is the total pressure exerted by air? Adding these gives a total pressure of 1 atmosphere, which you learned earlier is the atmospheric pressure at sea level. The ideal gas law, when used for a gas mixture, can be written as P total equals N total times RT divided by V. Dalton's discovery that each gas acts independently also enables you to use the ideal gas law to calculate pressure or the number of moles of any component of a mixture. For example, in a mixture containing gases A, B, and C, you can find the partial pressure of any of the gases by using the ideal gas law for an individual gas. If you want to find the partial pressure of gas A in the mixture, you can use the ideal gas law in the form PAV equals NART. Dividing both sides by V gives a similar equation as shown above for the total pressure of gases in a mixture. Have you ever noticed that a mylar balloon filled with helium stays inflated longer than a rubber balloon that is also filled with helium? The movement of a gas through a small hole into an area of lower pressure is called effusion. A balloon filled with helium eventually deflates as the helium inside the balloon effuses through tiny holes in the rubber or mylar. Helium effuses from rubber balloons faster than mylar balloons because the tiny holes, or pores, in rubber are larger than those in mylar, making it easier for the helium to escape from the balloon. In addition to the size of the hole, The mass of the gas particles also determines how fast molecules effuse. Have you ever noticed that balloons filled with air stay inflated longer than balloons filled with helium? This is because the air particles are heavier and much larger than helium particles. Thomas Graham, a Scottish chemist, studied the effusion of gases and formulated Graham's law, which states that the rate of effusion of a gas is inversely proportional to the square root of its molar mass. This means that the heavier the gas particles, the slower they effuse, and the lighter the gas particles, the faster they effuse. The effusion rate of different gases can be compared using Graham's law of effusion in its mathematical form. The rate of effusion of gas 1 divided by the rate of effusion of gas 2 equals the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. Compare the effusion rates of hydrogen and oxygen. The molar mass of hydrogen is 2 grams per mole, and the molar mass of oxygen is 32 grams per mole. If hydrogen is gas 1 and oxygen is gas 2, then the molar masses can be substituted into the equation so that the square root of 32 is divided by the square root of 2. The answer is 4, which means that hydrogen effuses roughly 4 times faster than oxygen. Let's review what you have learned so far. First, you learned that gases can be described using the 4 factors: numbers of moles, volume, temperature, and pressure. Next, you learned some physical characteristics of gases. Gases have mass and occupy space. Gases have indefinite shape and volume and therefore completely fill their container. Gases diffuse. Gases are compressible. Gases exert pressure, and the pressure gases exert depends on their temperature. Lastly, you learn the gas laws: Boyle's law, Charles's law, Avogadro's law, the ideal gas law, Dalton's law of partial pressure, and Graham's law of effusion. Putting all this information together, you should have an excellent idea of how gases behave. But why do gases behave like this? In the 19th century, after the gas laws had been formulated, scientists wanted to know more. They wanted to be able to understand and explain how the behavior of gases at the atomic level generated the observed behavior. In order to understand why gases follow a common set of gas laws, scientists were in need of a theory that explained the behavior of gases. A theory is a thoroughly tested model consisting of assumptions that explain observed behaviors. More specifically, in chemistry, a theory is an explanation of the way the behavior of atoms and molecules leads to the observed events that occur in nature and in the laboratory. Why gases behave the way they do is explained by the kinetic molecular theory. The kinetic molecular theory explains that matter is made up of particles that are in constant motion. This theory applies to solids, liquids, and gases, but this program will focus on how the kinetic molecular theory applies to the behavior of gases. The kinetic molecular theory makes 5 assumptions when explaining the behavior of gases. The first assumption is that gases are composed of particles, such as molecules or atoms, that are in constant random motion. This constant random motion is what gives gases their indefinite shape and indefinite volume. Constant random motion is also what allows gases to diffuse easily. A second assumption of the kinetic molecular theory states that the volume of individual gas particles is 0. This assumption is made because gas particles are so small compared to the huge amount of space separating them that their volume can essentially be ignored. The compressibility of gases is explained by this part of the theory. By decreasing the space between the molecules, gases can be squeezed into smaller areas. The third assumption of the kinetic molecular theory is that the average kinetic energy of a sample of gas particles is proportional to the Kelvin temperature of the gas. To understand this assumption, you need to know about kinetic energy. Kinetic energy, abbreviated Ke, is the energy of motion and is mathematically defined as half the mass of an object times the square of its speed, v. In this discussion, the object referred to is an individual gas particle. All of the particles in a pure gas have the same mass, but different speeds and therefore different kinetic energies. The graph on your screen shows a distribution of molecular speeds in a sample of nitrogen gas at 1273 kelvins. An increase in temperature causes an increase in speed for the gas particles, and a decrease in temperature causes a decrease in speed for the gas particles. Instead of talking about each gas particle, it is easier to average the speeds and discuss the average speed of the gas sample. Average is denoted by placing a line above the V. Using the average speed gives an average kinetic energy, also denoted with a line on top. The kinetic molecular theory assumes that the average kinetic energy of gas particles is proportional to the Kelvin temperature of the gas. Can you see how this explains why the pressure exerted by gases depends on temperature? The faster the particles move, the more kinetic energy they have, so the harder and more frequently they hit the walls of the container, and therefore the more pressure they exert. The fourth assumption of the kinetic molecular theory states that when gas particles collide with the walls of their container or with each other, they do so without losing any energy. The collisions are known as perfectly elastic collisions because no energy is lost. Normally, when objects collide, they lose energy. For example, when you drop a bouncy ball, each collision with the ground causes the ball to lose energy, so the ball does not subsequently bounce as high. A perfectly elastic ball would bounce back to exactly the same height after each collision. If gas particles lost energy every time they collided, they would lose energy and slow down so much that they would change into a liquid. Under normal conditions, gases do not just change into liquids, therefore the collisions of gas particles must be perfectly elastic. The fifth and final assumption of the kinetic molecular theory assumes that under normal temperature and pressure, the attractive forces between gas particles are negligible, meaning that gas particles neither attract nor repel each other. One of the properties of gases you learned about earlier was that a gas takes up the entire volume of the container it occupies. Since the attractions between gas particles are negligible, they occupy the entire volume of a container. To summarize, the kinetic molecular theory makes 5 basic assumptions about gases. First, it assumes that gases are made up of particles that are in constant random motion. Second, it assumes that the volume of individual gas particles is 0. Third, the kinetic molecular theory assumes that the average kinetic energy of the gas particles is proportional to the Kelvin temperature of the gas. Fourth, gas particles collide with the walls of the container and with each other without losing energy. Fifth, the kinetic molecular theory assumes that the gas particles do not attract or repel each other. Now that you are familiar with the kinetic molecular theory, let's see how well it explains the ideal gas law, which was derived from experiment. The kinetic molecular theory states that the particles in a gas are constantly moving. Gas pressure is a result of these particles colliding into the walls of the container. The number of times particles collide and the average force of each collision determine the pressure of the gas. Increasing the temperature causes the average kinetic energy to increase, causing both the number of collisions and the average force per collision to increase. Therefore, when the number of moles of the gas and its volume are held constant, an increase in temperature causes the pressure to increase. The kinetic molecular theory, agreeing with the ideal gas law, states that temperature and pressure are proportional. What happens if the temperature is increased while pressure and the quantity of a gas are held constant? The increase in temperature must be followed by an increase in volume to assure constant pressure. Therefore, volume is directly proportional to temperature. You should remember this as Charles's law. Now take a look at what happens when the number of particles is increased while pressure and temperature are held constant. Increasing the number of particles increases the number of collisions, which would increase the pressure, but the pressure in this experiment is held constant. Therefore, in order to keep the pressure constant, the volume must increase. The volume is therefore proportional to the number of particles. This should be familiar to you as Avogadro's law. Lastly, what happens when the volume is decreased and the number of moles and temperature are held constant? When the volume is decreased, the gas particles within the container are compressed. Since the temperature has not changed in this example, the average kinetic energy of the particles has not changed. However, the pressure increases because the same number of particles is contained within a smaller volume and thus hit the wall more often. The kinetic molecular theory suggests that pressure and volume are inversely proportional. You should remember this as Boyle's law. As you have seen, the kinetic molecular theory agrees with the ideal gas law. This is important because the ideal gas law comes from experiment. The better the agreement between experiment and theory, the better the theory. The kinetic molecular theory explains the behavior of ideal gases perfectly. But what about real gases? There is no such thing as an ideal gas. The gases in our world are real, and they only behave ideally under certain conditions. Gases behave ideally at room temperature and at a pressure of 1 atmosphere or less. As these conditions change, gases behave less and less ideally and do not follow the ideal gas law. This tends to happen at high pressures and low temperatures because under these conditions, assumptions made for ideal gases are no longer valid. The kinetic molecular theory assumes that ideal gas particles have no volume, although they actually do have volume. As you learned earlier, their volume is just so small compared to the space between particles that at low pressures, their volume is not significant. At high pressures, however, the particles of gas are pushed so close together that their volume can no longer be assumed to be zero. This is one way that real gases deviate from the ideal gases. Another assumption that is not valid for real gases is that gas particles do not attract each other. As you probably know, all gases can be turned into liquids at low enough temperatures. Particles in the gas phase are attracted to each other, but the gas particles are moving so fast that these attractive forces are not significant. When the temperature of the gas particles is decreased, the gas particles slow down, and the attractions between them become significant. At low enough temperatures, the attraction between gas particles becomes so great that a liquid forms. The attractions between real gases cause them to deviate from the ideal gas law. Although the kinetic molecular theory makes two false assumptions, it is still an excellent and simple model that accurately describes and explains real gases under standard conditions. An understanding of the gas laws and the kinetic molecular theory helped Jacques Cousteau and Emile Gagnon develop the equipment for scuba diving. SCUBA stands for Self-Contained Underwater Breathing Apparatus and allows people to breathe while underwater. At the surface of the ocean, air exerts a pressure of 1 atmosphere on a person's lungs. Once a diver descends to a depth of 10 meters, the water exerts a pressure of 2 atmospheres. For each additional 10 meters down, the pressure increases 1 atmosphere on the diver. At a depth of about 40 meters, a diver's lungs could not inflate, and the diver would be unable to breathe. Scuba equipment regulates the pressure of the gases a diver breathes so that the pressure inside the diver's lungs is equal to the pressure exerted against the body. This allows the diver to inhale a normal volume but at a higher pressure. Using Boyle's law, what would you expect to happen to the diver if she ascended quickly while holding her breath? Since the pressure against the diver's lungs would decrease, the volume of her lungs would increase, causing her lungs to rupture. To avoid such injuries, scuba divers must breathe while they ascend slowly. This concludes your study of gases and their properties. You now know that a gas is a state of matter that behaves according to gas laws. During this program, you learned several contributions scientists have made in understanding the behavior of gases. Boyle's law relates volume and pressure. Charles's law relates volume and temperature. And Avogadro's law relates volume and the number of moles. These factors all come together in the ideal gas law. You have learned that these experimentally determined laws are explained by the kinetic molecular theory, which agrees remarkably well with the experimentally determined ideal gas law for gases under standard conditions. However, gases do not always behave ideally, especially at high pressures and low temperatures. By now, you should recognize that many gases are important in daily life. In fact, some gases are even essential for life. Understanding the properties of gases has helped people to invent safety airbags, scuba gear, the internal combustion engine, and much more. As you leave today, look for all the different types of gases being used around you and think about how the kinetic molecular theory explains the behavior of these gases.